So welcome everyone to this seminar of the IBM series. Today we have Gavin Morley from the University of Warwick. So a little bit of introduction for those of you who were tuning in earlier. We were talking about his time in Tallahassee at the National High Magnetic Field Laboratory. But Gavin did his PhD in Oxford, and he started very early working on spin qubits, molecular spin qubits particularly. And then he joined the MagLab in Tallahassee. He did a postdoc with Hans van Tol, building the famous high field, high frequency pulsed EPR spectrometer, which is still running more or less as Gavin left in the second half of the early 2000s. And then here worked on also on electrically detected EPR for qubits in silicon. A work that somehow carried on at UCL in London, where he had a fellowship. And then after that, he started his own research group in Warwick, where he's still now. And he's, I think, a director of the Quantum Center or something. So he accepted our invitation to give a seminar here for the IBM, and the topic is NV centers in diamond for magnetometry and for some exotic detection of the nature of quantum gravity. So, Gavin, the floor is yours.
Thank you. Thanks so much for the introduction and for the invitation. I should say that high field pulse machine in Tallahassee is massively sort of Hans van Tol's work, and I was just there for 2 years helping a bit. But yeah, it's an amazing machine, and it's a user facility. So if you don't know, then you can basically just show up and use it. As long as you ask in advance, then you can bring your sample and use it. And I really just recommend that enormously, because the people there are great, and the equipment is great. Even if some of the restaurants have changed since 2006 when I was there. But yeah, so it's really exciting to be able to tell you about our research in Warwick, in the UK. So probably you might have heard of nitrogen-vacancy centers in diamond. I'm not going to assume that anyone has, and I will do a bit of an introduction on it, but it's become a very popular topic in quantum technology and in EPR, and using it's very much based on EPR, on optically detected EPR, and a lot of the basic fundamental stuff in terms of NV centers is now really well understood, and the exciting frontier for that area now is about what can we do with NV centers in diamond, and that's what I'm going to be talking about today, using it really as a tool, using the understood known physics of NV centers in diamond as a tool for doing some magnetometry, and also for this exotic fundamental physics goal of testing whether gravity is quantum. It's a very sort of ambitious long-term goal, as I'll tell you in a minute. So I want to thank all the great people in my team, and all the great collaborators, and all these marvelous, generous funding bodies who've been supporting us to start with. And here's a bit of an overview of what I'm going to talk about today. What are these nitrogen vacancy centers good for? So, I mean, they're good for various things. This isn't a complete list, but this is the stuff that I'm going to talk about today that we're focusing on in my lab. And first one is magnetometry, like I said. So we measure small magnetic fields, and we've particularly been pushing this fiber coupled design, which I'll tell you about. So the advantage of fiber coupling is that we can have a sensor head that's sensitive, and that we can move around and put somewhere where we want to measure something, and that's a great strength of this technique. And on this, then we're guided by this question: can we build something that people want? Because we're really trying to commercialize this, and people from the startup world have really helped to get the message out that, you know, in terms of when you're trying to commercialize something, then the key thing is to actually have something that people actually want and not just be trying to, commercialize some cool bit of science, but actually finding the, the niches where we're actually useful is really important. And so that's very commercial. And then this number two is really very different in spirit, because this is just fundamental physics. We're trying to do an experiment to crack open the most important open problem in physics. In my opinion, the most important open problem in physics is to understand how we combine gravity and quantum mechanics. So we've got gravity described by general relativity, and we've got, quantum mechanics, which is, part of the standard model. And there was ideas about how to combine them using things like string theory, but that whole field, I think, has been very stuck. And what it needs is experiments. And so we have some proposed experiments that would be very hard, and but will take a long time. But then they're certainly feasible, and we're working on them. And so I'll tell you about that. And the idea is to levitate a tiny diamond, and we are already, for a long time, we've been levitating these nanodiamonds in vacuum, which is a great first step. But to test the quantum nature of gravity, we want to have those diamonds be in a superposition of being in two places at once, which is super exciting. We haven't done it yet, but that will be very exciting if we can manage it. And so, as part of this, then that led us on to making nanodiamonds that are more pure than the existing stuff. And so that meant that we had NV centers inside which have got longer spin coherence and longer p2 times for the electron spins. And this is always key for quantum technologies. And these nanodiamonds are great for lots of applications, like they can go inside living cells. Living cells will eat these nanodiamonds, and then you can look, you use the NV center in the nanodiamond as a probe for what's going on inside the cell. And so that is already starting to be useful, or at least potentially useful for some medical applications. So that's what we've got on the menu. Now is a bit of background on NV centers in diamond. You might think that diamonds are normally transparent, and the ones that you get in jewelry are typically clear and colorless. But we like these diamonds that are really pink, and they're pink because they've got these nitrogen-vacancy centers in them. That's just, the diamond lattice is carbon, and if we replace one of the carbons with a nitrogen atom, we have it next to a missing carbon, and that's a nitrogen-vacancy center. And then it needs to be negative. It needs to capture a spare electron to be NV minus. And then once you have that, then you have this marvelous playground for doing optically detected EPR. This is like the key paper where they did this with single NV centers back in '97, and it's really grown to be a huge field, quite a big field. And the magic of these centers is that we shine in green laser light here from the right, and the red light that comes off, this photoluminescence, the amount of red light that's coming off, that tells you the spin state. And so I've written that here, that we send in the green light, and we get number two is this spin-dependent photoluminescence, so we can do optically detected readout of the spin. And also, the other massive wonderful thing about this is that just by sending in green light, we polarize this electron spin, and this is optical pumping. You get that in, you get all this stuff in other situations, on other samples, but it works very nicely in this NV center in diamond. Also, we have very long spin coherence times because the diamond can be very pure. It can be like pure to 1 part per billion, and there's low nuclear spin. background, because there's only like 1% of carbon is carbon-13 with a nuclear spin and so on. And so this is really an excellent material, an excellent sample to play with. And so the sort of experiments that everyone does with these NV centers is shown here. So in zero magnetic field, zero Gauss, you can sweep the microwave frequency, and you see this optically detected EPR signal here as a dip. So that's less red, less PL intensity, less photoluminescence intensity on resonance. And then, of course, as we increase the magnetic field up here, then we get Zeeman splitting, so that the two resonances split out. Okay, and now I've got a couple of slides sort of showing why this is, the mechanism behind this. So we have these energy levels within the diamond band gap. Diamond has a big band gap, so all these energy levels of the NV center are safely within the band gap, and these are the ground state levels. So it's an electron spin 1. So we can have ms equals 0 or +1 or -1 for the NV minus state. And then at room temperature, then all of these states are equally likely, because this splitting is this zero field splitting here is only about 3 gigahertz. So that's a small energy compared to room temperature. So you could start off anywhere in here, but then we send in green light and excite it up to this optically excited states. And if it starts in ms equals 0, then it ends up in ms equals 0. And then it decays back and emits a red photon, which we detect. But then if we go again, then, but instead of just sending in the green, we also resonantly excite with microwaves, and we flip the electron spin, then that changes things. So now the green excitation takes us up, from if we're in the +1 or the -1, we end up in the +1 or the -1 in the excited state. But then there's an intersystem crossing, which brings us over into these singlet states, these dark singlet states. And then the system gets stuck here for about 300 nanoseconds. And eventually, after 300 nanoseconds or so, it decays back. But in all that time, in all that sort of journey, it was stuck here for 300 nanoseconds without emitting any red light. And so because we flip the spin, it means that we are not measuring red light in that time. Whereas if we stay in the zero state, then we're emitting one red photon every 12 nanoseconds. And so you can see that then there's more red light when we're in the ms equals 0 state. And also this optical pumping happens, because if you start in the 0, then you stay in the 0. But if you start in the +1 or the -1, then you might get dumped into the 0. So after a few cycles, then we polarize into the 0 state. And so that's sort of the magic of the NV. And this is how you can do pulsed experiments with a single NV center. Equally, if you have a sample with a huge number of NV centers, like in these diamonds, then you get bigger signals, which lets us have more sensitive magnetometry. So yeah, these are the great things about the NV center: the spin polarization and the spin-dependent fluorescence. And these are the 3 electron spin states that we play with as qubits, or as for doing the sensing, the magnetic field sensing. This is just showing again the same idea, how it's all about the strength of the different transitions between these energy levels. And then this is the Zeeman splitting. So if we apply a magnetic field along the NV axis, then we get this energy level structure. And so in zero magnetic field, we get this one resonance at the zero field splitting of 2.88 gigahertz. And then in some other magnetic field, then we get one resonance here, and then a second resonance up to the +1. So that's these 2 transitions. And so then you can see already here that how we can do magnetometry. So we measure this spectrum here, then we know that we've got this magnetic field. And so this is functioning as a magnetometer, but in order to actually do sensitive magnetometry, we do way more fancy tricks. We do lots of fancy tricks, but sort of the simplest trick, the first trick, is just to sit on the resonance and use a lock-in measurement to sensitively spot if this resonance just moves left or right a bit. So that's the basis for the magnetometry. And like I said, we want to build something that is actually useful. We want to build something that people want. And so here is a long list of good characteristics of these diamond magnetometers. I'm not going to go through them all, but the fact that there are many, you can see, means that it's quite specific problem to really sort of find what are the applications that particularly need these great things. But we're looking at several applications. So this photo is me in front of a fusion tokamak experiment, and so we want to try and use these magnetometers for helping with future fusion power plant diagnostics. So, and this is, for example, using the fact that the diamonds are radiation hard, because fusion will be putting out a lot of high energy neutrons. Also, we've got some work coming out soon about medical applications in surgery, and we've got a paper where we're looking at trying to do navigation using a magnetic map. So if you have a map of your location with all the magnetic fields, then you can measure your local magnetic field and use that to try and know where you are on the map. Also, we're looking at trying to put these magnetometers into space for planetary, planetary science of other planets in our solar system, and also potentially satellites around the Earth. So yeah, here's just a list of our papers on this magnetometry stuff. We've got down to well, so this was our first one. This one, like I said, we've got this fiber coupled design. I'll show you a schematic of that in a minute. And then we've used it to see damage in steel, which is for looking for corrosion in steel. We got the sensitivity to 30 picotesla per root hertz, which is pretty much still the most sensitive fiber coupled diamond magnetometer. We did here the first tensor gradiometry. I've got some slides on all these things I'll show you in a sec. And we put it in the back of a van, as you can see here in the summer. So this is a schematic of what our magnetometers look like. So the diamond's here. The scooter is not part of the experiment, but this is supposed to be something that we're trying to look at. We're trying to study some object like a scooter, or could be a piece of steel, to see if there's corrosion in it or whatever. So we bring this interesting thing up to the diamond to use the diamond as a magnetometer. We put on a little bias field here, and then we send in green laser light through an optic fiber. We then get red fluorescence light coming back, which we separate off here with a dichroic mirror, and then detect that red light. The amount of the red light is telling us, the magnetic field effectively. And then we send in the microwaves for the EPR excitation to flip the spin, and we use lock-in detection. This is CW experiments where we're modulating the microwave frequency and doing lock-in detection to improve the signal to noise. So this is the schematic, and then the idea is that in this box here, with the dashed line here, we can sort of have some nice fancy equipment to get good, low noise performance. But then this sensor head here should be really small and lightweight, and we can move it around to go near the thing that we care about to see what the magnetic field is there. That's a schematic. Here's where I got one of these electric scooters off the street and brought it into the lab and jacked it up on some books, and we could see the magnetic field when we ran the motor, we could measure that with our magnetometer here. And this is Stuart Graham, who was doing the PhD student doing these measurements. He's just submitted a month or two ago. And so here's data from one of Stuart's papers where he got down to this 30 picotesla per root hertz sensitivity. So we can see these small magnetic fields. This is the noise spectrum where, you know, between 10 and 500 hertz, then we have this nice low noise. And, you know, and like I said, this is the most sensitive fiber coupled diode magnetometry. There is this other paper that got down to 12 picotesla per root hertz by having a similar magnetometer, but using these big flux concentrators to sort of concentrate the magnetic field from the environment onto the diamond. And that's a good technique for some applications, but does make your sensor head much bigger and takes away some of the coolness of it, because our diamonds are 1 millimeter cubed or less, and that means that we can get great spatial resolution compared to sort of things that are 30 millimeters in size. Okay, and here we got a video of our sensor head scanning over a piece of steel. So this is Alex Newman's work, where we're scanning this diamond sensor head over this piece of steel that's got some damage. We've put in these holes, we've put in this damage into the steel, and we can image that magnetically, even though the steel isn't very magnetic at all. And so we first were doing this in this 2021 paper with Ray Zhu and Raj Patel, and that was working fine. But in this new paper, Alex has added in loads of cool improvements. So one of them is that he's doing something called tensor gradiometry. So that means that in the first paper, we were not even measuring vector magnetic field. But in this paper, then we measure the vector magnetic field, Bx, By, Bz, but also we're measuring the gradient of, you know, there's 9 terms in this tensor, and we've got dBx by dx, dBx by dy, dBx by dz, and so on. So we're measuring the gradient of the x, y, z fields in the x, y, z direction. And in that way, you've got just more information to really better image the thing that you care about. And so that's cool. And here's some data showing that it's more useful. So here's an image of that steel plate. Here's the steel plate, and it's got these holes here. It's got 5 holes here, 5 holes here, which you can see as these patterns here, 1, 2, 3, 4, 5. But also in the middle, then there's these 9 smaller holes, and they get really small in this bottom right corner. And the vector imaging isn't really able to see the small ones. But here with the tensor gradiometry, you can see there's 1, 2, 3, 4, 5, 6, 7, 8, 9 little holes in the middle. And this is showing that the tensor gradiometry is giving us more information, letting us see things that we couldn't see otherwise. And then, like I mentioned, we put this is the magnetometer. We can make it smaller than this, but this was how we had it set up to put it into the back of a van. I was doing something useful by driving the van, and Stuart and Alex were doing all the physicsy stuff. And this again is a picture of the whole magnetometer that we could push around on a trolley to you know, to measure the vector magnetic field as we move around. And you know, and this could be useful for various things like navigation, if you've got a magnetic map, but also for useful for looking at the battery. If you've got an electric vehicle, then you could use this magnetometer to check on the charge or the health of the battery in your vehicle. Here's some of the data where we're driving it around near Warwick University, and we're measuring this magnetic field. And so this was us with our diode magnetometer. This was a measurement with a flux gate, which is a different type of magnetometer, just to show that there's good agreement between them. And again, here you see good agreement between the between our NV center measurement. This is BX, the X component of the magnetic field, is agreeing with the flux gate measurement of the same thing as we drive it around. Okay, so that's pretty much all I was going to say about the magnetometry. Feel free to shout out if you've got any questions about the magnetometry, because otherwise I'm going to change topic onto the fundamental physics stuff.
Kevin,
Yeah.
can I ask one simple question?
Yeah.
Where do you buy these nano-vacancy diamonds? Where do you make it, or do you buy it from a company?
Yeah, so we sort of depends on the diamonds. Some of them we're involved in helping to make. Some of them we just get them, already perfectly good as they are. So for all this nice stuff that I've talked about so far, we're getting the samples from Element 6, which is this company in the UK, and they, for this magnetometry work, then they've really sort of, I think, optimized the diamond and made it excellent. Yeah, and we don't really do anything for those diamonds.
So these are synthetic diamonds.
Oh yeah, everything's synthetic diamond. We're not sort of using any natural diamonds for this.
Okay. So my other question is regarding the energy levels.
Yeah.
If you look at you go back to your, sorry for that,
Sure.
The next slide, I think. Okay, here, yeah. So these energy levels, okay, the ground state is S equal to 0. The ground state is spin is 0.
So this is the ground state with spin S equals 1.
Ah, I got it. But the S is equal to 1, nitrogen has 3 unpaired electrons. P orbital, 1s2, 2s2, 2p.
Yeah. So the way to think about it is that so there's 2 electrons basically in this unpaired electrons in this defect, because we get 1 electron from this carbon atom, one electron from this carbon atom, 1 electron from this carbon atom, and then the nitrogen contributes 2 unpaired electrons, because it's 1 along in the periodic table from carbon. So that's 5, and then the NV grabs another electron from the environment, so that's 6 electrons, and then 4 of them pair up, and they're EPR silent, but there's 2 left that are in the S equals 1 state.
But nitrogen has a 3. If I'm correct, nitrogen is 1s2, 2s2, 2p3.
So I mean,
Carbon 6.
So the nitrogen only has you have to remember the nitrogen is bonded into the diamond lattice. It isn't shown here, but this. Sorry.
Okay.
So this I'm only showing these.
Yeah. I get it. Yeah.
Yeah. So the nitrogen's making bonds to 3 carbons that isn't shown, and then this extra thing into the middle is the nitrogen still has 2 unpaired electrons left that it donates.
Yeah, I get it. Now I get it. Thank you very much.
Thanks.
Thanks.
Yeah, I should maybe add in the extra balls for that picture. Okay, so let's get on to the levitating nanodiamond stuff then. So here's a whiteboard, and everyone probably has heard of the quantum 2-slit experiment, which is illustrated in this equation, where we can have a wave function saying that an atom can be in a superposition of going through the left slit and the right slit at the same time, and then you can see interference on the other side. And then a more macroscopic version of that was suggested effectively by Schrödinger in 1935, when he was talking about his cat, and he was saying, can a cat be in a superposition of being in 2 places at once, inside the house and outside the house? And we're not actually working on any cats, but we're interested in how far we can push it here in this space in between. What's the most macroscopic superposition that is possible in terms of, you know, having a heavy object with a big superposition distance. That's this distance between, you know, the cat being inside the house and outside the house. And so, you know, just experimentally pushing this boundary is very interesting for fundamental physics and potentially for other things as well. And then by doing that, you can ask, what is the gravitational effect from a mass in a spatial superposition? And we can already ask this because, like I said, you know, we already have experimental demonstration of the quantum two-slit experiment, where an atom can be in a superposition of going through the left slit and the right slit at the same time. And so we know that happens and that obeys quantum mechanics, but we can then already ask, you know, what's the gravitational effect of this atom that's in a superposition of being in two places? Because, you know, is something gravitationally attracted to, you know, to a superposition of the two places? And that's what you might guess if you come from a quantum background, but, you know, the best theory of gravity we have is general relativity from Einstein, and that is an entirely classical theory. And within general relativity, there's no way to just say that, you know, we're going to have a superposition of space-times. In general relativity, then gravity is all about, you know, curved space-time. So mass curves space-time, and that's what gravity is in general relativity. But general relativity is so totally classical, and there's no way, people have tried and failed to sort of, you know, force general relativity to be, you know, to be quantum mechanical. Except, of course, you know, there are attempts like string theory to do proper quantum gravity, but these sorts of things really need experimental tests. Here's my sketch of this, where if we've got a superposition of the cat being in two places at once, then do we get a superposition of two different curved space-times? You know, which would be one possibility that, you know, general relativity might suggest. But testing all this is, you know, experimentally is a huge, big, exciting opportunity for trying to crack this important problem in physics. And then the reason, you know, this has been a big open problem for 100 years, but the reason that this is exciting now is that there's this exciting work from Sagato Bose. He's a theorist in UCL in London, and he suggested this brilliant experiment where we could potentially test this with numbers that don't sound too crazy. And the idea is to see whether gravity can entangle two things. So here we've got one diamond here, which starts out at the top, and we need to put it into a superposition of being in two places at once. And then we do interferometry. So we bring the two spatial superposition components back together to, you know, do matter wave interferometry here. And then we have a second diamond on the other side here, which is also doing this matter wave interferometry. And it turns out that by looking for whether these two diamonds get entangled due to gravity, then you would be able to tell if gravity is quantum. And this would require roughly a 2 micron sized diamond. This is the superposition distance would need here. That would need to be about 250 microns. And this closest approach would be about 200 microns. The whole thing would take a few seconds. So these numbers don't sound outlandish, but they would actually be, you know, these are actually incredibly demanding, way beyond the state of the art. But we're, you know, we're excited to work on that. It's a very long-term challenge that's experimentally exciting. And this is the best, this is the most macroscopic spatial superposition experiment so far from Marcus Arndt's group. He has more recent results that are not published yet, but what this you know, research demonstrates is that you can do an experiment that is basically like the quantum two-slit experiment, but using molecules made up of 2,000 atoms. And so these molecules are in a superposition of being in two places with about 266 nanometer distance between those two places. And this is super impressive and exciting, but it totally just reproduces what you expect from quantum mechanics. So there's nothing nothing unexpected going on here. But yeah, we don't know, does this still, does nature still behave the same way when things get bigger? And so the diamonds that we're using are about a micron across, and they have about 10 billion atoms in them. And so it's really much more ambitious to try and go up to that size scale. We need to go up to that size scale to be able to try and study this quantum gravity question. And so we have a bunch of theory papers proposing how we'd like to do this. It uses the Stern-Gerlach effect, where the diamond starts at the top with one NV center in there, and we put the electron spin of the NV center into a spin superposition of pointing left and right. And then with an inhomogeneous magnetic field, we would get a superposition of forces, so that one superposition component is coming over to the left, and one superposition component is going over to the right. And then we'd have to recombine them, like I said, to do interferometry, to do measurements at the end. And we've been working on some experiments for this. This is Angelo Francescu in my lab. This is a vacuum chamber. Have a look inside the vacuum chamber. You can see this microscope objective, and here is a zoom of that objective, and we were doing optical trapping, and this green dot is one of our nanodiamonds levitating in vacuum. So that was working well, but then we were trying to pump down and reduce, the pressure, and it ended up not working. And we realized that the problem was that the diamonds were getting up to these high temperatures, and at these temperatures, then the diamonds burn in air, or they graphitize in a nitrogen gas environment. And so as we turn up the laser power, there's just too much heat going in, and the diamonds overheat, and in vacuum, then they can't dissipate their heat, and so they just get too hot and they get destroyed. So that was a real roadblock for us, but that pushed us to solve these problems. So one thing we did to solve these problems was to use much purer diamonds. So the commercial nanodiamond that everyone was using, is made from diamond with 150 parts per million, roughly, of nitrogen impurities. So the diamond is yellow, and that's bad for us because it's absorbing too much of the light, and it's yellow. It's absorbing too much of the light, and it's heating up. So instead, we bought these clear diamonds, 1,000 times more pure, from element 6, and my friend Ollie Williams' group in Cardiff, they turned these big diamonds into nanodiamonds, and then we did the optical trapping again, and now found that the diamonds were staying at room temperature for a pressure of 4 millibar. So that was good progress at the time. And then also that meant that we found much better spin coherence. And so here we're looking at nanodiamonds in electron microscopy, and then we can compare it here with our measurements using scanning confocal microscopy. So we know we're looking at this diamond. We saw it here in SEM, and now we are seeing it here with the ODMR, optically detected magnetic resonance. And then we can measure these long spin coherence times, like this is room temperature, measuring hundreds of microseconds, and these are, the longest spin coherence times for MV centers in nanodiamonds. And then we pushed it further with this new paper from James March, and these are sort of getting up to 700 microseconds for the spin coherence times. And so these are the longest, T1, T2, T2 star times for NV centers in nanodiamonds. And these are useful for, like I said, going into live cells perhaps, but also for our levitation experiments. Okay, and I'm coming to the end. I think I don't have time to tell you everything, of course. We have also done some magnetic trapping where we I can't remember, I don't have a slide on it here, but we've also done some diamagnetic trapping where instead of doing the optical trapping, we trap the diamonds using an inhomogeneous magnetic field, and the diamond is diamagnetic. So then we can, in that way, we can levitate the diamond without sending in lights, without sending in loads of heat. And so that's going to help more with getting these diamonds to keep cool as we pump the pressure down more. Anyway, that's just a flavor of this levitated nanodiamond work that we have, where we're aiming to test the quantum nature of gravity on a very long time scale. And we've shown that these pure nanodiamonds that we've made are useful for being more transparent and also for having longer spin coherence times. So that was this is my last slide. So I was talking about how we've built these fiber-coupled diamond magnetometers that are certainly showing great promise for lots of applications, and we're keen to explore if they would really be useful for diagnostics in a fusion power plant, for medical applications, for space missions, and for navigation, and for corrosion in steel, and so on. These are some theory papers where we've been proposing how we'd like to test fundamental physics with levitating nanodiamonds. These are some of our experimental papers working on the nanodiamonds with levitation and with measuring the long, super long spin coherence. So I'll stop there, and thanks very much for listening, and I'm happy to take any questions.
All right, thank you, Gavin, for this exciting and exotic seminar. These exotic experiments. It's very cool. It's the first time I've seen something like this. So I encourage the audience, if anyone has questions, to unmute themselves and ask directly to Gavin. So I would like to start. I have just a couple. So when you work with nanodiamonds, you gave the dimension, and how many spins are in that nanodiamonds, and do you work with ensembles of nanodiamonds?
Yeah.
Oh, sorry, of NV centers.
Yeah. So these are experiments here that we've done are with single NV centers. So we have, some of our nanodiamonds have a few NV centers in them, but for the levitated fundamental physics experiments, then we want just a single NV center. So we were mostly just looking for nanodiamonds with a single NV in them, and so yeah, that's what we have here. Yeah, for some of the other applications, like the medical application, well, for the medical application with nanodiamonds, where you want to put the nanodiamonds inside living cells, then you want more brightness. So you want to have many NV centers, like you would like to have, say, 100 NV centers in a diamond that's maybe 80, 90 nanometers in size. And so I think that's important to develop next, basically, is nanodiamonds with T1, T2, T2 star times that are as long as possible and this sort of size, but having more NV centers in to have more brightness.
My second question is actually on this slide. I didn't get what is the difference between the different nanodiamonds that you tested, the T2 basically. This
sure,
like XY84, for instance.
Yeah. Sorry, I didn't explain this. So This is the Harnecker T2
Okay.
type, just with the pi poles. This is dynamic decoupling using XY8. So here we're sending in 32 pi pulses to just extend the T2 time. And then this one, I didn't explain it, sorry, I was rushing over this a bit, but this was spin locking. So we do a pi by 2 pulse, about X, and then a very long pulse about Y. And then we find that is the spin locking is the best for getting the longest T2 time. People call it T1 row sometimes. Yeah.
And the colors, like the different nanodiamonds, are just different it's the same type, it's just different crystals.
Exactly.
Okay.
Yeah. So we're just trying to get some statistics by looking at different diamonds in the in this batch.
Thank you. Has anyone some question?
Kevin, sorry to bother you. I go back to the same question. That energy level, the 3 electrons are from the carbon. Sorry for that. Still, it's not clear to me. Yeah. It's like the 3 electrons are from the carbon, then 2 electrons from nitrogen.
Yeah.
So then you say the 6th electron is from where?
From the rest of the diamond, like could be that there's another defect, like a nitrogen defect, that's contributed one of its electrons.
From the neighboring one, or
Yeah, from some defect somewhere else in the diamond that's given up an electron, and so we've got an NV minus.
Oh, okay. Oh, okay. Okay.
So it's not electrically neutral.
Oh, okay. So now it's a total 6 electrons. 4 electrons get paired, then the other 2 electrons are unpaired. That's why you get S is equal to 1.
Yes, yeah.
Oh, okay. Okay. That's clear. Thank you. Thank you very much. Yeah.
Yeah. I can send you, if you want, the molecular orbitals later. There's in this paper here, then there's nice figure. This review here has nice figures showing the molecular orbitals for the showing why you get the S equals 1.
Yeah, thanks. Yeah. So I saw another paper from Germany, I think, they did some biological applications using nanodiamonds. They did some kind of liver tissue. They did some kind of imaging stuff, like, it's really cool paper. Of course, you know that, I think, okay, it's good.
Yeah, there's great work. Well, I mean, all this NV stuff started in Germany with Jörg Grastrup. I've got the paper here. So Jörg Grastrup started this off really in Germany. Also, Fedor Jelezko was there from the beginning. He's in Ulm now. Jörg was in Stuttgart, and yeah, so Fedor in Ulm is doing some of that great work on biological measurements in cells.
I saw another paper yesterday. I saw the paper that is in PNAS from a group called, his name is Romana. First name is Romana.
Yes, Schegel.
Yes. Yeah, yesterday.
Yeah, she's excellent. She's doing amazing stuff. Really, really close to the medics. Her work is really, really well engaged with the doctors and the hospitals, and actually finding, like I said, you've got to build something that people want, and that means really understanding what people want. And so I think her work's really great for that, for understanding the medical problems.
Thank you. Great talk. I enjoyed. Thank you.
Thanks.
Okay. Are there more questions from the audience? Give a few seconds. In the meantime, I thank you, Gavin, again for giving this great seminar. We are looking for more applications then of the MV. And yeah, thank you, the audience, for tuning in. And the next seminar for us is on November 6th, and we have Ilya coming up. All right, thank you again, Gavin.
Right, thank you. Thanks for the invitation, and yeah, it's fun to chat.
Yep. All right. See you next time.
Okay, bye then.
Bye.
Thanks.